Hello, this is Ryan Winterhalter, and I'm here to do my skill number 20 video for honors pre-calculus. So the problem says create a quadratic that opens down with one negative x-intercept and one positive x-intercept. That is where we get the x minus 4 and the x plus 2. We have our positive, which is 4, and our negative, which is negative 2, and then we multiply those together to get x squared minus 2x minus 8. But it has to open down, so we multiply by the negative 1 in the front to get negative x squared plus 2x plus 8 as our function. So now, if we want to go from here, the first thing we have to do is label the positive x-intercept as a, so a equals 4. And then we have to make b equal to a minus 1, so b equals 4 minus 1, which equals 3. So now we have to find the area, we have to estimate the area first between the graph of the function on the top and the x-axis on the bottom from the y-axis to b. X equals 3 here. And we are using 6 rectangles. So what we can do is we can break this down, and we know each rectangle is going to have the same base length. Each rectangle is going to be 3/6 or 1/2 units in length. So what we can do is we can break this apart and find our increments of 1/2. So we have 1/2, 1, 3/2, 2, 5/2, and 3, all right here. And we plug that in for x because that will give us the respective heights of the rectangles that we want at our certain increments. And now what we do, this is the length because they're all equidistant and they all have the same length here. The same base length is this. Their base lengths are all the same. But this part here, this part is all about the height of the rectangle at that increment of 1/2. So what we can do is we can write these out because we're using 6 rectangles. So we take the 3 and divide by 6. That gives us our increments of 1/2. Then we plug in 1/2, 1, 3/2, 2, 5/2, and 3, all of our different increments into our problem here to find the area of the rectangle. So this is the area of the rectangle that goes from 0 to 1/2. This is the area of the rectangle that goes from 1/2 to 1. And so basically what we are doing here is we are finding the areas of the different rectangles, and then we're going to add them all up together at the end to get what we get, to get a rough estimate, which is 185/8 or 23.125. Now we can write this in a simpler way. We can write this in sigma notation like this, and it's a little bit hard to see. I'll move it over this way. Okay, so when we write it in sigma notation like this, we have our same 3/6 increment at the front because that base unit stays the same. But then we plug in 3k/6 for x because the k, what k does is k tells us the term value. And the term value starts at 1, and in this case will go to 6 because we have 6 rectangles or 6 terms. Each rectangle can be thought of as a term in a sequence that we will all add together in our series. Now, 3k/6. Why 3k/6? Well, because if we plug in 1 for k to get our first term, we get 1/2. And then if we do 2, we get 1. So when we plug in numbers for k from 1 to 6, we get our increments of 1/2 that we want when we're finding the area of the different rectangles, and then we're going to add them together. So I can write it like this and plug in 3k/6 for x, and this is the same thing as all of these here added up. So they both equal 185/8. That is the rough estimate with 6 rectangles. Now, we have to determine the exact area in this same shaded region here. Rather than using a certain number of rectangles, what we're going to do is we are going to set it up like this, just like we did up here, but instead we're going to replace all 6's with n, because n is the number of rectangles, right? Well, if we're using 6 up here and we said we're not going to set a defined number to this because it's going to be infinitely large, then we can just plug in n for now. And what we do is we're going to simplify this here. We're going to ignore the sigma for a little bit and just focus on this. And so when we go through our steps here, first we make 3k/n times 3k/n, then multiply that by a negative to get negative k, or negative 9k squared over n squared. Then we multiply 2 by 3k/n to get 6k/n. The 8 stays the same throughout. Then we multiply by the 3/n to get this here at the end. Now, what we can do is so this is the same thing as this. We were just changing the order of these numbers around. These are both equal, and so we're just going to rewrite it this way. Now, when I rewrite it this way, I'm adding 3 individual parts together, then I'm adding the sum of those sums of 3 individual parts. Or what I could do is I could break this down further into saying it is just the sum of all the sums of the 3 individual parts. So for this one, we are going to take the sum of 3 things, and then the sum of 3 things for another term, then the sum of 3 things for another term, then add all those together. But for here, what we're going to do, these are the exact same things. This one, we are just going to take the first value for all 3 of those terms, say, and then the second value for all 3 of those terms, and then the third value for all 3 of the terms, and we're going to add them all up, and then we're going to take that answer and add all of those together. So these things are the exact same. Now, when we look at the back, I just rewrote this up here for the sake of being able to see it without having to flip the paper. What we can do is we notice that the negative 27 over n cubed is a constant, right? That is never going to change. That is always going to be the same. The only thing that is going to change is k when it goes from 1 to 2 to 3 and so on and so on. The same goes for here. 18 over n squared is a constant. K is the only thing that changes. And over here there is no k, so the 24 over n is still a constant. Now we know that when we have a constant, we are able to factor stuff out. So here we're able to factor out the negative 27 over n cubed, here we're able to factor out the 18 over n squared, and here we're able to factor out the 24 over n. That leaves us with these 3 things here. Sigma with n on top, k equals 1, k squared, k, and just 1. And from previous problems throughout this semester, we were told that we're able to substitute in this for that, and this for that. So when we do substitute those in, we get this. But we're able to cancel this out and make things a little bit easier. We can cancel both n's there. We can cancel out a little bit here to get 9 over n times n plus 1. Then over here we can simplify a little bit to get this. Now at the end we're going to add all these together because we aren't changing anything about the actual problem here. We're just making sure that we're still adding the 3 separate terms together. Now here, because n is getting infinitely large, we're trying to write this not in sigma notation so that it's easier to deal with. But here, n is getting infinitely large. And when a number gets infinitely large like this, we have to look at the degrees. So the degree for this one on the top is 2, and on the bottom it's also 2. Over here it's 1 and 1, and over here it's 0 and 0. So for each individual term, the degrees on the top and bottom are the same. And since for both of these terms, the degree is the same on the top and the bottom, focus on the leading coefficient because that is the only thing that matters.